We covered in the last class, what we covered was like we started with this description of electrons in an electric field, how we can describe the behavior of electrons in the presence of an electric field using the band theory of metals, right? So that's what we started with in the last class. And then the main conclusion out of this whole discussion, although we discussed a lot of things, the main conclusion of all these things was that the electrons which participate in the conduction or electrical conduction in any material are actually the electrons which are at the Fermi energy level. Only those electrons participate in the conduction of electrons in a material, right? So that was the conclusion from here. And then I introduced a couple of concepts which we will use in when we will when we will talk about free electron model or the quantum theory of metals. So first was effective mass of electron, how that can take into account the internal forces which an electron experiences when it is actually in a crystal in comparison to when it is in vacuum. So that is how we take into account the that is taken into account into the effective mass of electron, right? Then we also discussed very briefly actually that higher effective mass means there are stronger interactions which an electron is experiencing, and lower effective mass means that the electron is experiencing a weaker interactions, weaker internal interactions. That was actually all we discussed, and we did not go into much detail because actually if we want to have more discussion about effective mass, we need to talk a lot about density of states, how actually density of states also affects the effective mass. So we are not going into those details right now. This much whatever we have described, that much is enough for our discussion, for the purpose of our discussion. Then the density of states, right? Density of states is the concentration or the number of states per unit energy per unit volume, right? GEDE, basically this expression here, that that can describe the number of states in the energy interval from E to E plus D per unit volume of the sample. And then we actually used this expression for energy of an electron in a 3D potential well for coming up with the expression for density of states, which looks somewhat like this. Basically, density of states is proportional to e to the power half. When from the bottom of the band, when we are taking the energy from bottom of the band, GE's density of states comes out to be proportional to e to the power half. And from the top of the band, GE should decrease, right? We saw that in this figure also here, that GE has a maximum somewhere around n by 2 level, not exactly at n by 2 level, but somewhere around n by 2 level. GE or the density of states has a maximum, and then it starts decreasing again. For that, actually, if you want to take that into account, this here e to the power half will become e top minus e to the power half, right? So this much we discussed in the last class. Is there anyone who has any doubts or question from the
Yes,
people?
sir. Sir, can sir, can I unmute?
Yes, yes, you are
Means I
audible.
can speak. Okay.
Yes.
So, sir, the doubt is that, sir, here we considered N1, N2, and N3 are the numbers.
Mm-hmm.
Even in numbers, we have considered them as integers.
Mm-hmm.
So we get the discrete states, means
Mm-hmm.
2, 2, 1, 2, in the form of a square.
Mm-hmm.
Sir, when we are considering the volume and the area, na,
Mm-hmm.
then we say that this volume 1 by 8 4 by 3 pi and s cube is equal to the energy levels, and twice of this is equal to energy state.
Mm-hmm.
So, sir, that relation of equating volume area to the discrete level, because this is continuous.
Mm-hmm.
So that is, sir, that I am not able to understand how we are equating these volumes and areas to numbers.
Okay. Okay. See, the thing is that here what we have, first of all, I hope this should be clear that we can take n1, n2, n3 should be, I mean, to be integers, because in quantum mechanics, actually there are discrete states. We have already seen that energy levels are actually not continuous. Although in a metal they form a continuous band, but there is still a finite gap between two energy levels. So that much, that is, I think, I hope there is no doubt about that. Now your question is about actually the how we can equate these discrete energy levels to a quantity like volume which is continuous, right? That is the question. So the thing is that here, although initially we are taking this volume, let me get my laser pointer here. So although we are using this volume here, right? This volume we are using for calculating the number of states which will be having energy less than E prime. Now this volume is defined by these n1, n2, n3 integers, right? So when we are saying that we are taking this volume to be, to be the energy, that means actually we are still talking about the discontinuous states only. And then finally we are dividing this whole area by the volume of the crystal. So actually that completely takes into, like, neglects this effect of discretization which we have taken earlier, right? Because finally what we are getting is the number of energy levels, because we have already divided by the volume here, L cube, which was the volume. So that is why we are not, this effect of discretization that goes out of the picture. And also see, ultimately what we are talking, we are we will, let us say, there is some problem with the discretization, but ultimately what we are considered about is actually this dependence here. This constant which we are getting before this, that will vary if, we if we went in and tried to get a, some sort of discrete picture of the number of states. But we are not actually much concerned about this phenomenon here, I mean this constant value which we are getting. What is our more concern is this dependence on e to the power half, and that will not change. Because see, ultimately, even if, let us say, we try to calculate number of these squares which are within this circle, even those will be proportional to the area only, right? The higher the area, the higher will be this discrete number of points or discrete number of squares, isn't it? So that dependence on n prime, which actually depends on energy, that will not change because the area is definitely dependent on n prime here, right? So that is why this constant value may or may not change. I'm not sure about that, but we are definitely sure that this dependence on e to the power half, that will remain unchanged, even if we try to calculate the number of discrete points which are within this area. Okay, so that is why we can safely use this area and volume picture here, because main concern for us is this dependence on e to the power half.
Okay, okay, sir. Sir, one more thing. Can you go to slide number 18?
Yes. Ah.
Sir, in that the last line, number of states within the circle. So are these number of states or numbers of energy level?
Sorry, this should be actually number of energy levels. I will change this.
Okay.
Yes, it should be number.
Sir,
Yes.
one more thing, sir. Sir, the number of state basically means ना कि सर एनर्जी लाइन में तो एक पूरा कर्व आता है ना,
Uh-huh.
और स्टेट्स में मींस उसकी स्पिन वाले वो जो हम बॉक्सेस जैसे रिप्रेजेंट कर लेते हैं फिजिकली, तो
Correct.
वो स्टेट्स होते हैं ना.
Right. See,
ओके
state mean one state can be occupied by only one electron. Okay.
हाँ.
One energy level can have two states.
हम्म,
State is actually a description of an electron, which means that if we know the state of an electron, we know like where the electron is, and we know basically everything about that particular electron. And two states can never be exactly same. That comes from the Pauli's exclusion principle. Okay. Although one energy level can have two states, in that also the two electrons will have different spins. So they are actually not in same state, right?
ओके सर, गॉट इट.
Okay. There is another comment coming from someone. Let me- There is a Gauss circle theorem which states that in a circle of radius r, the number of lattice points is equal to pi r square plus an error term. Right. So basically, what we were discussing now, actually, some student has written that there is a Gauss. I will just copy paste here. Although I have not heard about this theorem, but it seems like it is useful here for our discussion. There is a Gauss circle theorem which states that in a circle of radius r, the number of lattice points is equal to pi r square plus an error term. So basically, what we are doing is that we are neglecting this error term here, which we have uh, which we have neglected in our calculations. We are only doing the calculation for this pi r square term, right? Thank you. So, any other question from previous class? Okay. If there are no questions, let me start with our further discussion. Okay. So, density of states, the definition of density of states is number of states, GED, basically this quantity GE times DE, that actually gives us the number of states in an energy interval from E to E plus DE per unit volume, right? If we know, like, let us see, if I want to calculate the number of electrons per unit volume, if I want to calculate this quantity, number of electrons per unit volume, and I know the density of states, which means I know the number of states in an energy interval per unit volume, then actually if we multiply this GEDE is the number of states in this energy interval. If I multiply this by probability of an a state being occupied, Fe is basically the probability that a state which is having energy E is occupied. If I multiply this quantity by F of E, probability of the state being occupied, then I will get how many electrons will be there, right? How many electrons will be there in an energy interval from E to E plus D, right? And if I want to calculate this number of electrons per unit volume in the whole band, then I will have to integrate it over the energy range of the band, isn't it? And that will give me the number of electrons per unit volume, and will be is equal to integration over the energy range of the band f of E times g of E times dE, right? That comes simply from the definition. We are going to see how we can have an idea about this probability that a state with energy is occupied. We are going to discuss in the upcoming slides. Density of states we already know. We know the density of the dependence of density of states on energy value. Sorry, how it depends on the energy, right? So let us try to see now this how we can define the probability that a state with energy D will be occupied. This is called, actually, this whole discussion which we are going to do, it is also known as particle statistics. Like, how can we know that how the particles are distributed in any volume, right? One model for that is Boltzmann classical statistics. As the name suggests, it is the classical form of particle distribution, right? So let us say we have two electrons which are at energy level E1 and E2. There are two electrons which are at energy levels E1 and E2, and with the wave functions psi1 and psi2. They come from infinite distance, and after that they start interacting with each other, right? They are coming and then interacting with each other. Just give me a second. Yes. So yes, these two electrons with energies E1 and E2, they come closer to each other, and they start interacting with each other. Interactions means it is sort of some sort of collision, right? After interactions, their energy levels and their wave functions will change, right? Because they are getting affected by each other, right? So let us say after the interaction, the two electrons which we get, they have an energy level of E3 and E4. they have an energy level of E3 and E4, right? Now, because we have assumed it is to be a classical distribution, like how it depends on the like how it behaves is the we are considering the classical nature of electrons. So that means we don't have to satisfy the Pauli's exclusion principle. Pauli's exclusion principle says that the two electronic states can never be same. So basically, two electrons can never have same electronic states, which also means that they cannot have same energy also, right? So that is why we are assuming that Pauli's exclusion principle is not valid here. Now let us try to see how we can come up with this Boltzmann classical statistics. So what will happen is that these two electrons are interacting and they are going into these two energy states E3 and E4. If the whole system is in thermal equilibrium, that means the forward reaction, which is basically interaction of E1 and E2, and they are going to E3 and E4, it should be equal to the backward reaction, right? So basically, if E3 and E4, they should be also going to E1 and E2. So the probability of these two events happening should be equal in the thermal equilibrium. From this condition, we can get this, right? P of E1, which is we are defining P of E as probability of finding an electron at energy E, or fraction of electrons at energy E. Those two are actually equal, right? The fractions of electron which are at energy E, that is actually equal to the probability of finding an electron at energy E, right? So then in thermal equilibrium, we equate these two probabilities, the probability of forward reaction to the probability of backward reaction, and that will be P of E1 into P of E2. That should be is equal to P of E3 into P of E4, right? So this condition we get from thermal equilibrium, and this is simply energy conservation. Initial energy before the reaction should be equal to final energy after the reaction. So E1 plus E2, this should be equal to E3 plus E4. There is a question, sir, but why Pauli's principle is ignored? Because it must be satisfied at all times in real situation. Yes, you are right. Actually, I mean, we will see there is another distribution, because see this. That's why the name itself says that it is classical. This is Boltzmann classical statistics. So actually, this Boltzmann distribution, it is applied in many other contexts also. Like even when we have a colloidal suspension, which is actually a macroscopic system, even they are actually particle distribution sometimes follow this Boltzmann classical statistics. So we are just introducing, and this is the assumption from the beginning itself. We are making it clear that this is the assumption. So wherever Pauli's exclusion principle is important to be followed, we cannot apply, of course, this Boltzmann classical statistics. There is another distribution which I will just introduce after this. All right. So from these two equations which we just wrote here, we can easily actually say that this kind of expression, or this kind of equation for P of E, or probability function, should satisfy these two conditions, right? If P of E is equal to E times exponential minus E by kt, you can simply substitute and see that this will be followed. These two equations will be satisfied by this probability distribution function. All right. And what it says actually is that probability distribution function, that is inverse, that is basically that decreases as the energy is increasing. So which means there will be lesser number of electrons as we go to the higher energies. And that is very intuitive also, right? That when we increase the energy, we have seen earlier also, there are electrons only up to a certain energy level, that is known as Fermi energy, right? After that, the electronic states are empty. So that is why that also comes from this Boltzmann distribution also, that if we keep on increasing the energy, the probability of finding an electron with that energy will be lesser. And if we want to calculate the ratio of two energy levels, how many electrons will be there in each energy level, if we want to calculate the ratio, it simply comes from this expression only, right? it so actually, yeah, somebody was asking why we are using this. In some scenarios, even in electronic cases, it can be applicable. Like if we have statistics of electrons when there are many more available states than the number of particles, you can visualize that, if you can imagine that if the number of states, available energy states, is much higher than the concentration of electron, then there will be very less probability that two electrons can be in the same energy state. So they will actually automatically follow the Pauli's exclusion principle. We don't need to take into we don't need to take care of Pauli's exclusion principle exclusively, like because of the less concentration of electrons, there will be already the probability of finding two electrons in the same energy state, that will already be very low. So that is why in the cases where the number of available states is much higher than the number of electrons, then we can apply these Boltzmann classical statistics. All right, we will see actually in the next few slides that why this happens. So now we talk about another distribution type, how this second expression. It simply came. Somebody is asking how this second expression came. If you, because see, p of n2 will be proportional to the p to the power e, right? So if you take the ratio of n2 by n1, then you will simply get e2 minus e1 right here. Here basically p of e is proportional to exponential of minus e. So from there, if you just take the ratio, you will get this expression. The probability of finding the electrons in energy states e2 and e1, that will be that can be calculated. The ratio can be calculated by simply substituting n2 and n1. We are taking n2 to be proportional to p to the power p of e. Okay. Now let us see, if we want to take into account Pauli's exclusion principle, what we have to do, right? So if Pauli's exclusion principle means the two electrons, no, yeah, no two electrons. I thought there was a mis typo. Sorry, there was a typing error, but here it is fine. So no two electrons can be in the same quantum state, right? So two electron states, they cannot be having same energy levels. So now if we want to calculate the probability of this reaction happening while following the Pauli's exclusion principle, let us try to see how we get this expression. Simply, like, basically, this is also coming from thermal equilibrium. In thermal equilibrium, the probability of forward reaction should be equal to the probability of backward reaction. Now, forward reaction is E1 and E2, they are interacting and they are going to E3 and E4, right? So, if E1 and E2 are interacting and going to E3 and E4, that means first of all, even if the probability of interaction of E1 and E2 will be f of E1 times f of E2, because there should be electrons in E1 and E2 states, right? So this will be the probability of E1 and E2 interacting. Now this is coming actually if they are going to E3 and E4 after the reaction. If they have to go to E3 and E4, that will mean that energy states E3 and E4 should be empty. They should be ready to be occupied, because if there are electrons already in E3 and E4 states, then this reaction is not possible, right? E1 and E2 will interact, but they will not go to E3 and E4 states if E3 and E4 states are already occupied, isn't it? So the total probability now for the forward reaction, that will be is equal to f of E1 into f of E2 times 1 minus f of E3, because this is the probability of E3 state to be empty or to be available for occupation. Similarly, this is the probability of E4 energy state for being occupied, right? So this will be the total probability of the forward reaction. Similarly, we can calculate the probability of backward reaction. Here, E3 and E4 electrons, they are interacting and they are going into E1 and E2 states, right? So that means there should be electrons in E3 and E4 states. Probability of electrons being in E3 and E4 states will be f of E3 into f of E4, and probability of E1 and E2 states to be empty is 1 minus f of E1 into 1 minus f of E2, right? So this equation we get from thermal equilibrium, because now we are following the Pauli's exclusion principle, right? Earlier this probability was different because we did not take into account the Pauli's exclusion principle. Second equation remains the same. This comes from conservation of energy. E1 plus E2 should be is equal to E3 and E3 plus E4, right? Now Fermi and Dirac, they gave this function basically. That's why it is known as Fermi Dirac function. If you substitute this function into these two equations, you will see that these two equations are actually satisfied with this function. This is known as Fermi Dirac function. Here you can see that there is Fermi energy also appearing in our expression, right? 1 upon 1 plus exponential E minus EF upon kT. Fermi energy, if you remember, Fermi energy at least at 0 Kelvin is that energy level up to which all the states are occupied by the electrons. Above Fermi energy, all the states are empty at 0 Kelvin. Any questions on this equation? If this equation is not clear, I can explain again. All right. If everyone is fine, then let us go to the next slide. So this is how we will plot at t is equal to 0 Kelvin. You can look at this expression. At t equal to 0, actually it will be minus infinity. Within the exponential, we will have minus infinity, right? Let us go back one slide. This will be actually minus infinity, and then the exponential will become 0, right? So f of e will be is equal to 1, isn't it? So that is why we get this kind of step curve at t is equal to 0 Kelvin. At t greater than 0 Kelvin, we will have the Fermi Dirac function will look somewhat like this, right? Now we can say that as temperature is increasing, as we keep on increasing the temperature, probability of finding the electrons in the higher states will increase. Intuitively also it is true, right? As you increase the temperature, you excite the electrons. There is someone on my account. Sir, please explain the Fermi equation again. You mean this equation, right? Again. I think you mean Fermi energy. So we have already defined Fermi energy as that energy level at 0 Kelvin, the energy level up to which all the states are occupied by the electrons. And above Fermi energy level, all the states are empty. That is called the Fermi energy. That is what the definition of Fermi energy is. As we keep on increasing the temperature, this curve will keep on shifting upwards, which means the probability of finding an electron is higher as we keep on increasing the temperature. Similarly, and especially here below the Fermi energy level, the probability of finding an electron will be lower as we keep on increasing the temperature, right? Because of course these are the electrons which are moving from below Fermi energy to the above Fermi energy levels, right? So that's why the number of electrons will decrease below Fermi energy and they will increase at above Fermi energy level, right? Another interesting fact which actually comes is if this E minus EF, this temperature, this energy difference from Fermi energy, if it is much greater than KT, if it is greater than like much bigger than KT, then Fermi Dirac function behaves almost like Boltzmann function. You can see from here actually that if let us say E minus EF is much greater than KT, that means this exponential will go to infinity. Or actually, sorry, this will be, we can use the Taylor's expansion. Is it minus exponential having minus or not sign? Let me just check that. Yes, yeah, that is fine actually. So here we can say this will be infinity. So we can ignore this one, right? And this will be simply e to the power minus times e minus ef by pt, which is also what we got very similar expression in Boltzmann distribution function. So for energy levels which are much above the Fermi energy levels, this Fermi Dirac function behaves almost like a Boltzmann function, right? We can see from here. If this is much greater than kt, this one can be ignored or one can be neglected, and then this will be equal to e to the power minus ef by kt, right? That is another observation which we can get from this Fermi Dirac function. Another thing is at t greater than at t greater than 0 Kelvin, probability or probability function is equal to 0.5 at Fermi energy, right? At Fermi energy, f of ef is equal to 0.5. So from here, actually, we get another definition of Fermi energy, because right now what we defined Fermi energy, that was only for 0 Kelvin. At 0 Kelvin, all the energy states below Fermi energy are occupied, and all the energy states above Fermi energy, they are empty. But what about at T, at temperatures greater than 0, right? So there Fermi energy is defined as the energy level at which finding an electron, the probability is 0.5. Fermi energy is that energy for which probability of occupancy is half at T greater than 0 Kelvin. That is also another definition which is used sometimes for defining Fermi energy level. At 0 Kelvin, I already explained that f of Ef will be is equal to 1. That you can simply get from here, like if E minus Ef is less than 0, basically we are at energy levels below Fermi energy level. That means this will be at, and temperature is 0, right? That means this will be minus infinity. This means exponential will be 0, so probability will be 1, right? F of t will be is equal to 1 if energy is less than ef, and f of ef will be is equal to 0 if e is greater than ef, right? Because this will become plus infinity. Plus infinity means f of e will be is equal to 0, right? So all the energy states below Fermi energy are occupied, and all the energy states above Fermi energy are empty at 0 Kelvin. Is that clear? Any questions? Any questions about these observations which we just made? No questions? All right. Then let us go to the quantum theory of metals. We have been actually building up only for discussing this theory, all these three terms like effective mass of the electron, the density of states, and now this Boltzmann probability sorry, these probability functions, they all will be used in quantum theory of metals. So let us look at these four figures here one by one. Okay. At 0 Kelvin, we just discussed. At 0 Kelvin, all the energy states, this is our Fermi energy. This is the Fermi energy level. Alright. At 0 Kelvin, what will happen is that all the energy states will be occupied below this level, and all the energy states above this energy level will be empty. Right? But above 0 Kelvin, any temperature which is above 0 Kelvin, due to thermal excitation, right? There will be some thermal energy in the electrons. Because of those excitations, there will be some electrons in the energy states above Fermi energy, right? There will be some electron concentration available above the Fermi energy level, right? And this, how we can find these number of electrons? Let us discuss that now, right? First of all, we have this curve for density of states, which is basically g of e times dE, basically gives us the number of energy states in the energy interval from E to E plus dE, and that is proportional to e to the power half. This particular portion, that is proportional to e to the power half. For our discussion, actually, we will be limiting ourselves only up to these energy levels. We can see actually, because most of the interesting things are done within this interval here only. So that's why we will be limiting ourselves up to this energy level, and for that we can say that density of states will be proportional to e to the power half, because above this it should be e minus, sorry, e dot minus e to the power half, right? So but we are not discussing this part here, we are only discussing this portion here, because that is the most interesting part which we are interested in. All right. So the density of states, that is proportional to e to the power half in this domain here, and then it will reach to a maximum point. Fermi-Dirac functions, which actually tells us the probability of an electronic state to be occupied as a function of energy, right? So if you can see here at the x-axis we have the probability, and y-axis shows us the energy range. Sorry, the value of energy at. So if you plot this If we take this point, it will give us, and project it here, it will basically give us how many energy states will be occupied at the energy level E1, right? This is the significance of this plot. And earlier we saw that, right? The number of electrons, if we try to find the number of electrons in at an energy level, let us say in an energy interval, then we can write n is equal to, sorry, sorry. If we want to write the energy levels, n will be is equal to, sorry, this should be P or F, whatever you want to use, P of E times G of E times D, right? If you want to find the number of electrons in an energy interval from E to E plus D, that will be given by P of E times G of E times D of E, right? Sorry, DE. So this is what actually we are plotting. If we multiply that, actually this means if we multiply this density of states with probability function, we will get this functional form of n of E, right? Which is actually, this we can ignore. This is some misprinting here. This is only n of E, right? This curve will give the function n of E. We have not integrated yet actually. We are just multiplying these two functions. P of E, which is actually here f of E, into G of E. And that will give us this plot. Now, if we want to calculate the number of electrons, let us say in an energy range from E1 to E2, if you want to get the number of electrons, that we can simply get by this area, or basically simple integration of this curve, right? If we integrate this over this entire energy range, we will get the number of electrons which are there from the lowest energy to the highest energy, isn't it? So that will give us the number of electrons, and that is what is written in the second point here. Number of electrons per unit energy per unit volume, that is G of E times F of E, which is this function which is plotted here. This is number of electrons per unit energy per unit volume. So from here, if we want to calculate number of electrons in an energy range, Ne versus the area under the Ne versus E curve on the energy axis is the concentration of electrons in the band. Concentration is basically per unit volume, how many number of electrons we can have, right? So that will be given by the area under curve when we take on the energy axis, right? So that we can calculate by the simple integration. This we have already discussed actually, that for E less than EF, F of E is equal to 1. For actually, for any temperature, we discussed at zero temperature, but any other temperature also, if energy is much below the Fermi energy level, the probability is 1, right? You can see here the probability is 1. And so that means energy, this n of E will be directly proportional to E to the power half only, because F of E will be is equal to 1. So this function here, that's why you can say, you can see actually that this is almost like a parabola here, right? Up to a certain energy, it is almost like a parabola, because at energy levels much below Fermi energy level, F of E is equal to 1. So that means n of E, that becomes proportional to E to the power half, and that's why we see this kind of parabolic dependence. All right, and after that actually it decreases very sharply above the Fermi energy level. N of E also decreases very sharply, because this probability function that also decreases very sharply above, after the, once we have crossed the Fermi energy level, this electron concentration function that also decreases very sharply. So I mean, basically, the takeaway from this slide, although we have discussed a lot of things, the takeaway from this slide is, most important thing is that if we want to calculate the number of electrons in any energy range, that we can calculate from G of E times Fe, basically by the area under the curve. In this plot, if we calculate the area under the curve, we will get the number of electrons per unit volume. All right, and this, of course, all other things also are important, that what is the scenario at 0 Kelvin, what is the scenario above 0 Kelvin, why we have electrons above Fermi energy level at temperatures greater than 0, because of thermal excitation, right? Now let us see if we want to calculate the number of the concentration of electrons in a band. I just explained basically if we integrate from 0 to top of the band this particular quantity any times dE, which is equal to Ge Fe dE, we will get the number of valence electrons, right? Total number of valence electrons we can get by simple integration of this. We know we have already derived the expression for density of states. We know the expression for density of states, and we also know the probability distribution function, which in this case, because it is the electrons which we are talking about, they definitely need to follow the Pauli's exclusion principle. So we know we will use Fermi-Dirac statistics in this case. So if we substitute these two quantities here, G of E and F of E, which we have already derived, we will get this sort of expression, which is written here. Now, if you look at this expression very carefully, you can say that actually this is the concentration of electrons, and we also have Fermi energy in our expression. So actually this expression is relating number of electrons or concentration of electrons with Fermi energy, right? That means, because experimentally it is difficult to calculate directly the Fermi energy, but this expression tells us if we know the concentration of electrons, then we can derive, or we can calculate the value of Fermi energy also. There is a question, sir. G of E has maximum at approximately n by 2 energy level, but here it is seen it is greater than n by 2 because temperature greater than 0 Kelvin. No, see, I said approximately n by 2. So the question is actually somebody is asking that why do we see this maximum above n by 2 level? Like, it is, I think it is slightly above n by 2 level. But I never said actually that the maximum will be at n by 2 level. It will be around n by 2 level. It cannot be. What I wanted to say earlier also was that the maximum will be somewhere between, like, between the two extremes. At the extremes the probability will be lowest, and somewhere around n by 2 level we will have maximum density of states. So it is not that actually, if I probably communicated, if I confused basically, but the thing is, there is no certain position of this maximum. It will depend on a particular material, but it will always be around, it will be closer to n by 2 level than any of the extremes, than the minimum or the maximum levels. That's what I actually wanted to convey earlier also. Okay, so you should not be confused that why the maximum is above n by 2 level, right? It can be above or below sometimes also. It will depend actually how is the distribution of these density of states. If they are distributed more, like, if the concentration of density of states is, if density of states is higher in this region, then of course the maximum will shift lower. If the density of states is higher here, then the density of states will shift higher at higher levels. So that will depend on every material. Is that clear? Okay. Yes, so what I was discussing is we get an expression where actually which is relating the concentration of electrons to Fermi energy, which gives us one handle to calculate Fermi energy, because sometimes it may not be directly possible to calculate Fermi energy. And it also tells that the Fermi energy and concentration of electrons, concentration of valence electrons, they are very closely related to each other, right? They are actually dependent on each other. So now this expression is not very easy to integrate. You can see that actually this expression, the integrand, it is not very easy to integrate. One thing actually which you should ask also, why we changed this limit. Earlier the limit was from 0 to top of the band, but we changed it to 0 to infinity. Why that is happening is, you can see from here actually, as we go away, anyway, if we when we as we keep on approaching infinity or higher energy levels, Ne is approximately 0 only. So we can simply convert, instead of using top of band, we can convert it to infinity level. So we can integrate from 0 to infinity without losing any accuracy, and actually it makes our job of integration a little bit easier. That's why we change this limit from 0 to top of the band to 0 to infinity. At 0 Kelvin, actually, we can integrate this integrand here, right? At 0 Kelvin, below EF level, above EF level, basically, there are no energy states, which means F of EF will be is equal to 0, right? So there are energy states only below Fermi energy level, isn't it? And in that case, this will become minus infinity. So basically, we will have only e to the power half d within the integration, e to the power half times d, and then we can simply integrate. We will get this expression, which is actually for Fermi energy at 0 Kelvin. Fermi energy at 0 Kelvin, that is related to concentration of electrons in this particular fashion. All right. Now, although I already mentioned this integration is a little bit complicated, but if we use certain approximations which we are not we are not going to do this integration here in the class because it is out of the scope of this, I mean, for our discussion. But if we use some certain approximations, and once we integrate, we will get this sort of expression for the Fermi energy at any temperature. Fermi energy at any temperature, that is related to Fermi energy at 0 Kelvin, and there is this expression within the brackets, right? So what do you think? Like, how is the dependence from here? Actually, we can get the dependence on of Fermi energy on temperature, right? Because there is a temperature term also here, isn't it? We are getting how the Fermi energy is varying with respect to the temperature. Now, this value kT, usually it is very very small than Fermi energy, because usually Fermi energy is of the order of some tens of electron volts. Fermi energy, it is of the order of tens of electron volts. But this kT you can calculate for any temperature up to even for room temperature. If you will calculate, it is of the order of, I think, 10 to the power 3 electron volt, or basically some milli electron volts. So you can see actually that this term will be very very small for any temperature which we will use. This kT by EFO term, it is very very small. That means Fermi energy depends very weakly on the temperature. It is more or less constant, isn't it? It remains at the EF0 level, basically at most of the at any temperature, because this ratio kT by EFO, that is very very small. That's why the dependence on Fermi energy on temperature is very very weak. And now, actually, since the second chapter, I have been repeating that energy of electron or the velocity of electron is independent of temperature. Now we have come to that point where we can see why that happens. Why the energy of electron is weakly dependent on temperature. Because if you see the average energy, if we want to calculate, let us say, average energy of an electron, that will be defined by this expression. This is a typical expression for calculating the average of any quantity, right? If you want to calculate the average of average energy of electrons, it will be simply integration of E times NEDE divided by NEDE, because this NEDE is number of electrons, isn't it? And E times NEDE will be the summation of energy of all the electrons. So if we calculate this at 0 Kelvin, you will get the energy of electron to be 3 by 5 times EFO, and average energy of electron at any temperature will be 3 by EFO, and then again we have this term appearing in the expression for energy of electron also. All right, and as we have explained, kT is usually much much smaller than EFO. Okay, that is why the energy of an average energy of an electron, that is also very weakly dependent on temperature. For all practical purposes, we can say that the energy of electron changes very very small. I mean, the change in the energy of electron is very small with respect to the temperature. That's why so far we have been assuming, I was telling earlier that we will see this in next chapter, and now we have seen why actually we take the energy of electron to be independent, or very weakly dependent on the temperature, because this average energy of electron is very weakly dependent on temperature. All right. and this was not possible without using these quantum mechanical concepts like density of states and distribution function of electrons and only Fermi energy electrons contributing in the conduction. That we will see actually in the next topic. But density of states and effective mass as well as probability function, they are all very important to see this why the energy of electron is independent of temperature. And because in energy like in the metals, the electrons are moving very completely freely within the crystal. That means the average energy is actually their kinetic energy only, because freely moving electron means they don't have any interaction or they don't have any potential energy. So whatever energy they are exhibiting, that is purely kinetic energy. So we can simply equate the kinetic energy of electron with 3 by 5 times EFO, and that will give us the root mean square velocity of an electron, and that will depend on Fermi energy of the electron, and basically it is insensitive to the temperature. All right, we remember that if we have taken the kinetic molecular theory, right, that then the energy of electron should be 3 by 2 kT, isn't it? Which is directly proportional to temperature, but that does not happen in electrons because kinetic theory assumes that there are no interactions which an electron is having. But in this case, we know that electrons are having interaction from each other as well as the ions which are present in the metal. So that's why we cannot have this kind of this kinetic molecular theory for electrons, and the velocity, average velocity of an electron, that comes out to be independent of temperature. Yes, whatever we have discussed actually here, wherever you are seeing this ME, mass of electron, everywhere ME is actually effective mass of an electron. I am not using ME star, but wherever this ME is appearing, we should take it as effective mass of the electron. Here also, everywhere, wherever we have ME expression, I will mention that in the slide also. But you should remember that in this expression, in even in Fermi Dirac function, we don't have mass of electron, but in density of states, we do have mass of an electron. That should also be effective mass of the electron. I have mentioned that actually in the slide also. So wherever we have this ME, we should use effective mass of the electron. Then we have already taken potential energy in account. Yes, exactly. It is there. That is true. So somebody is saying because we are using effective mass of an electron, that means that we have already taken into account the potential energy of electron. That is true. Whatever small part of potential energy will be there, because we saw that for some metals the effective mass is very low, some for some metals effective mass is very high. So we have taken already potential energy or the internal interactions into account by using the effective mass of an electron. Any questions so far? This is very important actually what we discussed, because so far we had been simply saying that the velocity of an electron is temperature independent, but here we can see how it happens because actually this particular kT by EFO, this expression, right, this ratio is very very small. That's why we get very weak temperature dependence of Fermi energy as well as energy of electrons on temperature. Any questions? Okay, there are no questions. Then we will stop here for today, and we will meet tomorrow in the class. Tomorrow we will start with, like, we will use this theory for deriving conductivity of a material, the quantum conductivity of a material, and then we will discuss the some, like, significance of Fermi energy, how Fermi energy actually plays very very important role in a lot of practical applications which we see day to day, but we don't pay attention to them. So we'll discuss uh, all those concepts in the next class. Okay, thank you. See you all tomorrow.